Good morning. It's my pleasure to be here to introduce Reuben Olinsky. So I'm Galen Hunt. I used to run the operating systems group here in MSR. I'm now, since the invite went out, I'm now part of Azure as well. And Reuben used to be part of MSR OS group as well, and he's a part of Azure, although he's been in Azure for about 3 months longer than I have. Really briefly, it really is quite my pleasure to introduce Reuben. Reuben joined MSR back in 2009. Before that, he was in the Windows setup team. And when he joined, the very first week that he joined as an engineer in our team, I said, well, I'm leaving to SOSP. I'll be back in a week. Here's a JTAG. Here's a phone. The network stack doesn't work, and Experiment 19 doesn't boot. But it'd be great if everything worked when I came back. And Reuben had never used a JTAG debugger before. I don't think he'd done any driver development. He had been in the kernel before, but not a lot. And I came back a week later from SOSP, and Reuben had the networking, the phone was booting, and the network stack was running, and he'd worked miracles. And he's been working many, many miracles since then. He's going to talk to you about Drawbridge. Particularly, Drawbridge was started with an intern's name? Don Porter, who's now a professor at SUNY Stony Brook, and I started as an intern project. And I got it as far as we could show Excel, which you'll probably see today, but it was what we would call in research an egregious hack, or what people outside of research would call an egregious hack. Inside research, we would describe it as one Bond star. So we had a demo that held together long enough to write a paper. And then Reuben joined the Drawbridge team and added a whole bunch of engineering discipline and experience and architecture, and has built something that we're getting ready to ship. Now, one thing I do want to remind everybody, this talk is Microsoft confidential. In particular, Reuben's going to be talking about some of the ship targets and things. We have not disclosed outside of Microsoft. There have been no public disclosures about the fact that Drawbridge technologies are tech transferring into products or productization plans. So just everybody, we do have a academic paper that describes the core technologies, but none of the productization plans are public knowledge. And so please remember to keep them as Microsoft confidential. Anyway, it's my pleasure to give you Reuben.
Thank you. Thanks for the far too kind introduction. Here today to talk about Drawbridge. It's our project for sandboxing Windows apps at extreme scale. As Galen mentioned, I'm a developer in the Azure OS team, and until about March, I was working in MSR Redmond's operating systems research group. So without further ado, I want to give you basically a quick elevator pitch of what our project's all about. So Drawbridge is a new virtualization technology for hosting isolated Windows applications. So what does that really mean? Specifically, we're a project trying to take a lot of the benefits of hardware virtual machines productized in such Microsoft offerings as Hyper-V and be able to shrink them down to rapidly, significantly decrease overheads. Specifically, the main benefits we aim to provide are, one, secure isolation, the fact that you can run separate applications in their own isolation containers and feel safe knowing that they can't compromise each other nor the host on which they're running. Two, persistent compatibility, the idea that you can take your application, you can package it up with all of its dependencies, perhaps inside a virtual machine image, run it in its isolation container, and know that changes to the underlying host won't be able to break that application once it's been packaged up in that way. And three, live migration. The idea that you can have a running application and it may start on one particular physical machine, but once it's wrapped up in its isolation container, you should be free to move it from host to host, from physical machine to physical machine, without it even being aware or in any way cooperating with this motion. As I mentioned before, we aim to do so without the full overheads of hardware virtualization. Specifically, our goal is to be able to run, and what we'll show you today is being able to run hundreds of isolated applications per physical machine instead of perhaps on the order of 10 or 20. Being able to provision, start up these applications on the order of seconds instead of perhaps minutes or hours, and being able to take snapshots for live migration and for suspend and hibernate and resume, generally on the order of these snapshots being around 10 megabytes, kind of close to the size of an MP3, as opposed to what you might get with the save state of a hardware virtual machine, which might be more like size of a DVD, something like hundreds of megabytes or order of gigabytes. And specifically, we aim to be able to run unmodified Windows applications. This means unmanaged, managed applications, trusted or untrusted, but that no requirement is placed on being able to recompile or change the application in any way. Before we proceed, I see a question in the back.
So is it a goal to reduce the steady state overhead or only the overheads that you list there?
The goal to reduce the steady state overhead or the overheads listed here. What do you mean in particular by steady state?
So for example, the amount of CPU or memory or the I/O performance hit of running a VM.
So I guess informally I'd say, our target is to be comparable to kind of the CPU performance that you might get with hardware virtualization, but really focusing on these kind of fixed costs that go into, that are kind of baked into uses of hardware virtualization and make those go away. So that's sort of the quick elevator pitch. Before we proceed too far into technical details or architecture, I actually want to show you a quick demo. Kind of get that showing up front so you can see it's real, see it in action, and have kind of a real scenario in the back of your mind. Specifically, what I'd like to show you is something that's very, very specific to actually what we're trying to accomplish in Azure around high-density web server hosting. Escape out of my PowerPoint for just a second. So what I'm going to do here is I'm going to launch 100 securely isolated IIS web server instances running in their own Drawbridge isolated instances. I've launched Process Explorer over here on the right so you can actually see what's going on in real time. You can see in the few seconds I've been talking, we've already got these 20 or so instances. So the way you should think about this is these are completely and securely isolated from each other. Perhaps 100 different external customers asked Microsoft to host a website on their behalf and run it in our Azure data center. So maybe these websites are mom and pop websites or a family website, something that gets hit maybe a few times a day, maybe only a few times a week. Clearly these aren't going to be things that are going to be spinning the CPU. We're going to want to pack these things in as densely as possible for operational costs, and so that we can kind of give as cheap as possible functionality to our customers. And also to put this in perspective, what we have here is we've got most of these 100 instances running so far. I'm going to launch a web browser just so you can see one of them in action. And if we were to have done the same thing with, let's say, Hyper-V, it would have required on the order of 10 different physical machines to accomplish just what my one 8 gigabyte, not particularly special laptop has been able to do in a matter of just a minute or so. So what you're seeing on the left here is I've launched a native copy of Internet Explorer, just browsing to one of these sites. And one of the reasons this is taking a little while is we're actually starting up everything from scratch. I have a very simple ASP.NET site loaded into each of these servers, listening on different ports. And here, what you've witnessed is we actually went back and we launched a copy of the IIS worker process. It actually had to go and compile the website. It found C# code, launched the C# compiler, launched the resource generator, created some binaries fresh for that instance, loaded up those binaries into the worker process, and connected them up to the request so that the web browser could connect to it. So that's sort of the quick pitch here. I see a question.
The same with having a separate website which runs its own process. What's the difference between this one?
So the question here was, what's the difference between this and just running a separate website in each process? That's an excellent question. We've got a great slide kind of covering what the, for instance, Windows process model looks like and why you wouldn't want to use it as your isolation boundary for being able to run multiple tenants that are mutually distrusting and which are distrusted by the host system. In our case, the representative scenario here is that Azure is the host and some random person on the internet who might have even gotten this website for free and provided whatever binaries they wanted to is providing the code to run inside these containers. So just like that, I'm also going to quickly terminate the demo. Head back to our presentation. So who are we? Galen gave you a little bit of a background to kind of put some more details here. We started up a feature team in the Azure Operating Systems team around March, and we're now at the point where we have somewhere between 3 and 4 developers, 1 tester, and 1 program manager working full-time on making Drawbridge a reality and actually shipping it within Azure. Our goal is shipping it within this fiscal year. In fact, we have one particular customer lined up, and their scenarios look very similar in idea to what you just saw in that demo. Another point, I know it's sort of blatant, but we have to say it. We are hiring and looking for good, sharp people. If you know of anyone, feel free to spread the idea around. We'd love to have more people join us and help out. So this project did start as a research project in the operating systems research group in MSR, where both Galen and I came from. Started as an intern project and took an evolution a long time. It's shown up at TechFest a few times. You may or may not have seen it in some state at that point. Ongoing research is continuing within MSR. At the very end of the talk, I'll just give a quick pointer to some of the ongoing, more speculative projects that are going on outside of the product realm. All right, so now we're going to dive into our approach and actually get into some technical meat of what's going on here. So when you think about isolation, obviously it's natural to think about hypervisor-based virtual machines, hardware-based virtual machines. They do come with significant overheads, as I alluded to before. They're the resource overheads of the gigabytes of disk space, the hundreds of megabytes potentially of pinned physical memory per virtual machine instance. They're the runtime overheads of CPU virtualization and so on. Administrative overheads, just the fact that you're actually, in the case of Microsoft's technology stack, you're managing a completely separate copy of the Windows operating system in each of these isolation domains, in addition to one for the host. It's a lot of overhead there just in terms of administration, plus the cost of moving these very large images to and from the cloud and on-premise and the customer site. Of course, however, they do provide significant benefits. They do securely isolate all guests from each other and from the host. They do support such advanced and very critical data center features as live migration. And in fact, they're the only isolation mechanism that is strong enough to be able to enable the cloud to host multiple tenants and do so safely. Obviously, the question here is, can we retain all of these benefits, but somehow look at different trade-offs to decrease the overheads? And some of the insights in particular that we're trying to arrive to were, well, do all applications need to see a full virtualized view of hardware? Or do they just need higher level services that's enough for them to complete their work? Obviously, that won't be true for every application, but for a large class, quite possibly so. Additionally, do all apps require their own instance of an operating system that they choose themselves with their own specific set of hardware drivers? That may be true for some set of applications, but certainly not true for a vast majority. So another sort of point along the isolation scale one might look at, and there's a good question about before, what about processes? So, for instance, one could look at the processes inside Windows, the NT processes. They are lightweight. They do a good job of isolating address spaces. They can scale to thousands. You can organize them into higher structures, and they've been around since the operating system was constructed and designed. Unfortunately, they really aren't strong enough for cloud hosting. The interface between a Windows process and the host is on the order of at least 1,200 functions. I say at least and because at runtime this number can even increase with additional loaded drivers that expose ioctls or custom controls. So it's a very, very large interface between each process and the host. Very, very hard to get right and to secure. Additionally, the state for a given Windows process isn't actually contained within its own address space. The state for that process actually lives spread throughout the system. Of course, there is memory within its own address space. There's also state on behalf of the process inside the kernel. There's distributed state in various background user mode services. And suffice it to say that if one wanted to be able to support functionality like live migration, where it's really important to be able to take an application and isolate all of its state, it just would not be feasible with the current Windows process model and existing applications hosted on them. And finally, and perhaps most importantly, the Windows process model was architected for, at most, friendly multi-tenancy. The idea that you might have terminal servers and you might have multiple different users from the same corporation logging into the same server, and, well, what if one of those users starts hogging too many resources or doing something bad? Well, you can always kick them off. You can fire them. You can have the IT department actually terminate their sessions. There's a very different model for how you deal with those threats and a very different set of threats. The cloud threat model, however, where you're actually having anonymous potential hackers out on the internet with unlimited access to run code of any of their choosing on our systems right next to all of our trusted and valued customers. The NT process model is not enough to be able to secure against that threat.
Are other production operating systems any stronger in terms of their process isolation?
Are any other operating systems stronger than the isolation? I'm assuming your question is this inherent to Windows or is this inherent to the way processes are implemented in modern operating systems? I'm not really an expert in probably any modern operating system other than Windows. I would speculate to say there probably are some inherent kind of issues across the board where while it's always a nice idea to be able to keep that state tightly isolated, in practice for real world systems, there's going to be kind of your state spread all over the place just for user experience, for simplicity, for multiplexing, for sharing, for all those sorts of reasons. But again, I'm not really an expert, so I don't know if I can properly qualify that.
Yes, I was wondering, what is the advantage of Drawbridge over, say, things like vServer, right? Because have you heard of vServer in Linux? It's
could you say a little bit about it? I'm not quite familiar.
Yeah, it's a kernel-based isolation mechanism where.
Well, so there are other like jails and
Yeah.
those. Let's assert that they provide adequate security. They're roughly the equivalent. What they don't provide is the persistent compatibility, right? You have to run the OS that's running inside the security boundary is the same as the one outside the security boundary. They don't provide live migration either. And so what we have with Drawbridge is a solution that lets us have as good as you can get security in any other operating system, and in addition get the persistent compatibility and the live migration capabilities of a VM.
Good question.
So that actually reminds me of the work by Jason Mead about ZAP, right? Their concept of pod.
It's pretty similar.
Pretty similar.
Particularly, they did a really good job with the encapsulation of the state, of at least the file system state. And
So basically, they were solving the same problem for Linux.
yeah. Yeah, I guess I don't think they address the persistent compatibility issue or be able to do the live migration. But they did a much better job of kind of, jails gives you process isolation, but doesn't necessarily give you full, how do you compose a file system? And Jason's work really addressed how to.
Linux kind of pervasively doesn't care about persistent compatibility. They don't give you that on the host platform either.
Yeah, that's true. Good point.
So, talked a bit about processes. Question here is, can we use what we do get from NT processes, but with a stronger isolation interface, so we can get each of these three properties that we've been discussing? Brings us to the Drawbridge approach, and want to sort of start out explaining what our key design philosophy is. The idea here is that we start from a point of security and from a point of isolation. We start with this very tight and tightly controlled secure isolation boundary. After we've got that set up, then we add back in application compatibility so we can run unmodified applications. And we do all this app compatibility work inside the isolation container so that the changes we make for compatibility don't in any way have an impact on, cannot have an impact on isolation. Another way to put this is we're not trying to plug holes in an existing interface that already is compatible. We're starting off from a point of security, not from a point of compatibility, and trying to reintroduce isolation. So the key components we use to implement this philosophy are the Pico process, it's our isolation mechanism, and the library operating system, which is our compatibility mechanism. And I'll talk about that in just a second. So the Pico process is a concept introduced by previous work at MSR, and it's a fairly straightforward idea and concept. It's an isolated address space with a very, very small and very fixed interface with its host, ideally to be used as a lightweight isolation container. So the second major component, what we actually choose to run inside that Pico process, is the library operating system, a concept that many of you are most likely familiar with, a concept that's been around in the literature for quite some time. The core idea is that you do have a minimal shared kernel that runs in supervisor mode of the processor, but its sole responsibilities are really around managing hardware, around presenting an abstraction of that hardware and multiplexing the hardware for various different user mode processes. So the next piece here is that the library operating system actually runs entirely in user mode. It constitutes the remainder of what a lot of us think of as the personality of the operating system, all the different API services and libraries and frameworks that run in the address space of the process. Of course, this means that each application can choose its own library operating system, and the library operating systems can coexist peacefully on the same underlying kernel. I'm going to move to our implementation based on the ideas we've discussed so far. So how do we implement a Pico process on Windows? So we did start off with the Windows NT process. Obviously, as I mentioned earlier, this NT process has a very large interface with the host, so that's our first step. Entirely remove that interface with a very, very minimal change to the Windows kernel. And in fact, this is the only change we needed to make to the core Windows kernel. We're able to block all existing system calls that a traditional Windows process can make, both to the NT kernel or to the kernel mode subsystem of the kernel mode component of the Win32 subsystem. At this point, then we have an isolated address space running on Windows that can't do anything, can't get outside of itself. From there, we add back in our very limited system call interface, these 45 system calls that comprise a portion of the Drawbridge application binary interface. The important thing to realize here is that there's no way to break out of the address space without going through one of the system calls we've added back in. There's no way to somehow subvert it with a hard-coded trap or sysenter instruction. These 45 routines are the only way to get out of the process. So we've described to you kind of what the Pico process looks like. Now I want to move and talk about, well, what does that interface with the host look like? As I mentioned, we have the Drawbridge application binary interface, the interface between a Drawbridge Pico process and its host. There happen to be right now 45 down calls and 3 up calls. Everything else is off limits. So the interface was designed from scratch. It's not a subset of any existing API set in Windows, although it was to some extent inspired by some of the design patterns in NT. As kind of an example, I have some of the APIs listed here on the right. And for instance, you can see there's a routine for virtual memory allocation. In fact, it looks almost exactly like the routines that exist in Windows, virtual alloc EX or NT allocate virtual memory. The main departure is we've removed all of the parameters that allow you to specify which process you'd like to allocate the memory into. We obviously don't allow you to talk about anything outside of your own environment. Something else important to call out is that the APIs all have fixed and closed semantics. There are no ioctls or any of these kind of expandable interfaces that can at runtime suddenly gain all manner of unstructured parameters and functionality. So you can look at this interface in our system and if you look at it the right way, it's analogous to the interface between a host and a guest in a virtual machine. Obviously the main difference here being at a significantly higher level of abstraction. Instead of presenting virtual CPUs to be scheduled by the guest, instead we directly present an abstract notion of a thread from the underlying host. Instead of presenting physical memory that has to be managed and paged by the guest, we present virtual memory. And instead of presenting a virtual view of device hardware and device registers and device I/O space, we present a high-level construct we call an input-output stream. So some of the benefits of how we've cut things, sort of one, for security reasons, we believe and assert that this interface is small and fixed enough that it can undergo exhaustive and manual inspection, testing, penetration to gain a level of confidence about the quality of the implementation in addition to the design. Secondly, for portability reasons, something that may seem a little bit subtle is that we are able to run any Windows application that's unmodified. Any Windows application that's able to run within the Drawbridge environment can run anywhere that these 45 functions are implemented. This is the sole bottom API service that's required to be able to host a Windows application. I'll get to sort of the implications of this in another slide. And thirdly, for a point of flexibility. So the way we've designed the interface is we've designed it to be as stateless as is possible, the idea being that all of the state for the process lives within the address space of the process itself. Obviously, this is not true or possible for everything And in those exceptions, we've made sure that the state that lives elsewhere can be pulled back out by the process and inspected and retrieved at runtime, so we can be able to do a live migration or suspend and resume. Question?
Do you have a rule of thumb for which system calls you put in and which you don't? If somebody comes along and says, sure, it would be nice if you put this extra call in there. How do you evaluate that?
It's a good question. The question is, how do we evaluate what this interface ought to look like, and what's our metric for deciding should a new API go in or out? Certainly our thinking on this evolved significantly over time. At first it was whatever we needed to do to get things up and running that also seemed relatively small. Over time, then we took a hard look at kind of trade-offs between performance and simplicity of the interface. We're sort of at a point now where we are fairly stable. I don't know if we have anything in writing, but the general thinking is that major concepts that are key to this interface, kind of the concepts I explained earlier, APIs to interact with those concepts belong in this interface, provided that functionality couldn't otherwise be easily and in a performant way derived within the library operating system itself. We also do have a mind toward looking at, hosts other than Windows, and looking at, are these APIs actually going to be feasible to implement in a reasonable way on a variety of hosts? It's been a little bit kind of give and take and trial and error along the way. I don't know if that really satisfactorily answered your question. That's sort of the decision-making process we're using right now.
So related to that question is, there must be no free lunch, right? What did you sacrifice by only including this small set of system calls, this small API there? What
did we sacrifice?
Yeah.
That's a good question. So there's another slide later which will help explain more of kind of how do we still get back up application compatibility and what sacrifices or not we make there. Obviously, introducing any level of abstraction, there's always going to be some amount of performance overhead, and at some point there's the trade-off between the isolation we're able to achieve and the performance overhead, much in the same way that you get that with hardware virtual machines as well. Application compatibility and performance are clearly two big concerns always. I'll talk a little bit more about application compatibility later. Question?
Probably a missing point. How much is it possible to run a non-Windows guest OS, or get one non-Windows guest OS using this pattern, or is this pretty much designed and maps like almost identical to NT concepts?
That's a very good question. The question is, could you run something other than a Windows guest inside on top of our Drawbridge host? And the answer to that is yes, we believe so. We haven't yet completed that existence proof, but in fact, some of the ongoing work that's happening in MSR is to explore aspects of that nature. We do have, actually, I will get to that right now. So this is the slide I was alluding to, talking about portability and flexibility. So we do have non-Windows hosts we've certainly cared about. So those have been an excellent way for us to make sure that we're not letting Windows-isms slide too much into this interface, and we're not doing something that would really make it impossible to do something in a non-Microsoft or Windows way. There's additional work that'll probably need to be done to iterate on that interface to make sure that we can suitably support non-Windows library operating systems as well. So this is just sort of a range of some of the various different prototyping or more than prototyping projects that have gone on to host a Drawbridge Pico process and library operating system on a host that might not look quite like Windows. Obviously, the one we care most about in Azure, Windows Server 2008 R2, and very shortly Windows Server 8 as being our kind of flagship hosts that we're productizing. But there's a variety of other projects that are interesting for various reasons. Question?
So through this interface, can you expose then some custom hardware that host OS has?
If you wanted to, could you expose some custom hardware that the host OS has? That's a good question. I guess one way I would put it is it might depend on what that hardware looks like and how you want to expose it. Obviously, it's an interface. You can always expand it, but we are very careful in doing so. Instead, one thing that we've gone to when trying to expose physical or virtual devices is to use this IO stream abstraction and find out can that abstraction fit on top of? Can you build some kind of a proxy that allows you to either direct or mitigated access to whatever the device is in question? So you can still guarantee kind of the same isolation principles that went into this design of this interface are maintained. as specifically, right, the risk of giving unfettered access to some specific host resource is very scary. So doing so within the interface we've provided is the way we'd recommend. And we do believe it's possible for, like I said, hardware devices that could be exposed as some kind of a byte read-write stream.
So doesn't the I/O stream approach kind of explode the security surface again? Because you could be passing any data through there and multiplexing it out to any driver, which you don't know what it's going to do with it.
So the question there is, well, by having these I/O streams, doesn't that just give you an escape hatch to the rest of the world? So that's a good point, and it's certainly something that has to be carefully maintained in the implementation. So our implementation of our I/O streams are very careful to only provide, actually, the way we've implemented things is it's not even the I/O streams themselves, but there's a layer above them that doesn't even allow access to I/O streams unless the right access checks have been done, the right isolation checks have completed. I'll get more to how our security monitor and our host actually does that policy work. The idea there, yes, it does allow you access to various different parts of the system. The other bit there, though, is that there isn't a binary contract where you can call a method, get back values, and sort of pointer-based interfaces. It's still a flat serial data stream, which at least is a step up.
So does the registry sit above the application binary interface? Or
Question about where does the file system sit, where does the registry sit? I'll get to that in a little bit. Is there another question in the back?
Yeah, so how massive is the work for doing a library OS or doing a host? So they walk up to you and say, do Windows 8 for a host, do Windows 8 for a library OS, which of those is scary and how scary?
That's an excellent question. So the question was, what's the incremental work to move from, let's say, one version of a host to a new version, or one version of a library OS to a new one, or potentially also, what's the work required in just porting it entirely? So we've got some data points that might be easier to go into the finer details offline of the work required, let's say, to port and support Drawbridge on the Barrelfish Research OS that Andrew Bauman works on along with other folks, or what it's been taking to get the same working on Midori. So we do have some data points there. In terms of kind of moving incremental version releases, we actually started off building our library OS and host for Windows 7, the original Windows 7 RTM release to manufacturing bits. At some point, then we did a move to Windows 7 Service Pack 1. Now, servicing release of the Windows operating system isn't a significant departure, but there's quite a bit that changes. Just to give you a sense of what that work went into that, it took about 2 to 3 hours of dev time to make that transition. Moving from Server 2008 R2 or Windows 7 to Windows 8, we expect would take a bit longer than that, but it's not going to be sort of years of time. It's going to be a much smaller amount of time, for sure. And obviously that's something that we will be doing once Windows 8 actually releases to manufacturing. Does that answer your question? Okay. All right. So we've talked about the isolation container, its interface with the host system, and now it's time to talk about the Windows library operating system that we've built. So key here is, well, to avoid kind of sacrificing what you get when you run a Windows application, we want to be able to have as high application compatibility and performance and reliability as possible. The main design approach here is, well, why don't we just grab as many original binaries from Windows as possible? In fact, if we had our druthers and with enough time, we'd take all of the binaries from Windows unmodified, or the subset that are interesting to the application. More interestingly, perhaps, is that we've really made sure to stick with the same architecture. So I have a very simple, perhaps not quite simple, diagram on the right. This is the architecture of Windows. This has nothing to do with Drawbridge. This is just the way Windows looks, with kind of kernel mode components at the bottom, user mode at the top, applications and frameworks higher than that. So what we did when trying to build the Windows library operating system was effectively take this existing architecture and move it up inside the Pico process. Another way to look at this is that we've enlightened Windows to run efficiently and correctly inside a Pico process, right alongside the application it's supporting. That means we're able to lift a lot of the code up into user mode, even code that traditionally runs inside the kernel in Windows. An example that we've built here is this Windows 7 Service Pack 1 library operating system. And it's about 100 megabytes of binaries on disk, and it's running time overhead just for having a private copy of these various different services in each Pico process is on the order of 16 to 20 megabytes of working set per application. And just for some other statistics, there's millions of lines of code that kind of went into this port. I see a question in the back.
Yeah, is there really a kernel user boundary inside the Pico process?
Good question. Is there a kernel user boundary inside the Pico process? So the true transition between kind of user mode and supervisor mode is actually at the very bottom of the Pico process. It's in invoking one of those 45 system calls that we expose as part of the Drawbridge ABI. However, we do have, as we call it here, a virtual boundary primarily to preserve the architecture and layering of the existing Windows system, where we've actually introduced our own user mode kernel that's the counterpart to the existing NTOS kernel that runs on a Windows system. And we've got virtual drivers like win32k.sys and http.sys and ksecdd.sys, which happen to be running in user mode, but be exporting and importing the traditional kernel mode interfaces of the Windows system.
So it's structured like a kernel, but there's no protection of the kernel from the user app.
That's correct. The insight here that this fellow made is that there is no protection between our user mode kernel and the components that live above it. If an application corrupts memory of our user mode kernel, that application will bring itself down.
And basically the kind of intuition that drove that was that kernel is only serving one application, and so we don't need to protect it from the application.
Question in the back?
I noticed it says application exe at the top. What if your application is more than one exe?
So the question is, what about multi-process applications? It's an excellent question. In fact, you've to some extent already seen one. When we were running our IIS web server, in fact, there's this w3wp.exe, it's the web worker process. It spawns off the C# compiler, csc.exe, and the C# compiler spawns off a resource generator, and so on. Now, it turns out that works well in Drawbridge because those processes don't share a significant amount of state or count very much on implicit sharing. Their sharing is mostly through a shared virtual file system, through command line arguments, through environment variable block, and kind of things of that ilk. So we're able to still get by with this kind of per Pico process user mode kernel. So there are limitations in place in sort of the V1 implementation of Drawbridge and how we've built things, where certain multi-process applications that may be split into multiple address spaces, perhaps for kind of lifetime management or fault isolation, those might not work exactly the same way in Drawbridge at present in our implementation. There are ways around it. We're actually able to, for instance, what we're doing today, hosting a copy of lsas.exe, which typically runs in its own user mode process. We actually happen to host it in the same address space as the actual application executable. So we sort of do have more creative ways of doing things, but it is a limitation of our present implementation.
The kernel there doesn't really do what a full kernel does.
The question there is, the kernel doesn't do what a full kernel does. What do you mean by the second half of that?
Well, there isn't, like, it's not managing virtual spaces within the virtual space.
A kernel does three things: muxing, abstraction, and protection. It doesn't do muxing because there's no multiple guests. It doesn't do protection because they just said everything is in one package. It does do abstraction, so the app thinks it's talking to the classic Windows API, and it's not.
That's right. I mean, it's primarily present in our system for application compatibility, so we can actually run unmodified Windows components above it. Question? Yes?
One other question. So you said that one of the big drawbacks of virtual machines is that the memory space that they take up, which I thought was because you're running redundant copies of the OS. But here, it sounds like, so why couldn't you get the similar savings if you sort of customized had a library OS running on a VM instead?
So the question there is, well, we stated that some of the concerns with hardware virtual machines, significant overheads of running redundant copies of the OS, but here we are still running multiple copies of our user mode kernel. Couldn't we not have just tried to shrink the actual operating system? So there's sort of a couple comments here. I can speak at least with a little bit of knowledge around Microsoft's virtualization offerings like Hyper-V. With Hyper-V, each guest is actually given physical pinned memory and is not allowed to overcommit. I know there are sort of features like dynamic memory and other kind of fancy things like that sort of mitigate it slightly. But the practice is that each kernel does require that physical memory. It's still responsible for paging. It's still responsible for a host of various different responsibilities that require quite a number of runtime structures, of overhead, of state, as well as just kind of code size and components. And there is that portion that we don't have to run at all, we don't have to pay for at all, because we've taken a lot of the traditional responsibilities of the kernel and we've just moved it out into the host, where we already have one copy of the underlying host that's sort of able to load up driver stacks and manage the actual hardware and kind of do that amount of work. So specifically, our user mode kernel, it doesn't need pinned memory, it doesn't need pageable versus non-pageable. It just needs virtual memory, and that virtual memory can actually end up getting paged out to disk. So you could run significantly more user mode kernels and Pico processes on the system than you might even have available RAM or physical resources for. I don't know if that partly answered your question. Of course, one could also go and try to reduce the size of an OS, and that's still going to be good too.
There's really kind of two benefits we get out of this over the alternative approach. We actually did we did have Silas Boyd-Wickizer came in as an intern and built an implementation that would run Drawbridge on top of Hyper-V in a bare VM, each VM and each Pico process in its own bare VM. There's two key benefits we get out of this design. One of them is it costs extra cycles and resources to maintain the hardware virtualization itself. Okay, just VT, you've got an extra layer of protection. There's extra overheads that are involved in that. The other one is because because of the abstraction layer that we provide, we're able to exploit a lot of the sharing that resource sharing that happens within the host operating system. So for example, the file cache, we can make complete use of that. So we get much, much more efficiency out of sharing the file cache, sharing read-only copies of pages and things, without having to go through all the groveling around trying to match diff pages and doing all that complexity that other systems do.
One more question.
But it seems like by sharing those information, there might be like side channels, right? If you're concerned about, say, privacy of like separate instances, there might be still some leakage going on, right?
So we would certainly be susceptible to kind of timing-related side channel attacks. I touch a page, I figure out if my fault causes someone else, if I can see someone else's fault, then we are susceptible to those kind of attacks. We're not, there's no data visibility, but there are those kind of side channel information.
That's true.
Timing attacks, we are susceptible.
That's true. I mean, the same thing goes for file cache. Like you can figure out which files are being accessed by other programs, right? By just measuring the timing it takes. Because if it's in file cache, it will be faster.
Yes, there's a whole branch of attacks there. And also I'd say smart VMs that, smart resource VMs that are, say, doing memory compaction have exactly those same
problems.
Vulnerabilities, right?
All right, I think we've talked enough about this. The only last point I wanted to mention is that, much like the library OS concept, with Drawbridge, each application can have its own library operating system, its own kind of virtual Windows running within its address space. Similarly, the version does not need to match. So you don't need to have the same version of Windows in our library OS up in user mode that you actually have installed on the bare metal machine. All right, so we've talked about the isolation container, its interface with the host. We've talked about the library OS to run inside the isolation container. Talk just for a few minutes about our implementation of the host on the Drawbridge host on Windows. So our host is our implementation of these 45 APIs and the rest of the ABI. And you can sort of think of it as being analogous to the hypervisor and virtualization stack in Hyper-V. Also taking a page from Hyper-V, we also split up our implementation into two pieces. Within kernel mode of the actual physical host, we run a driver along with our very slightly tweaked version of the Windows kernel. And we also have a security monitor that runs up in user mode that we're able to dispatch to make policy decisions and be able to kind of farm out all of our higher level decision-making work and policy file parsing work into user mode where it's a safer place to be. The general split is that, as I mentioned, it's only consulted for these policy decisions. So the user mode piece, the Drawbridge security monitor, it's simultaneously fills the roles of being the application that launches a Pico process and the one that serves up these policy decisions during the process's lifetime. it is just a normal Windows process and has access to the full Windows API set and functionality surface. It is, however, part of our trusted computing base. So the policy decisions at present in our security monitor are based on simple text file manifests. So by default, the Pico process has access to no external resources beyond its address space. From there, we bring back in resources that have been whitelisted. So resources can be whitelisted in this manifest file. And here's just a kind of a simple example of some of the resources that you might be able to list in. You might, for instance, be able to map in a folder from your physical host file system and map it into some different location in the virtual file system. So this serves here both as access control and a way to do virtualization so you can prevent information disclosure, and also for compatibility reasons and for kind of multiple instancing. You might have named pipes or TCP sockets or endpoints that you want to allow the Pico process to access so it can listen on a port, or so it can connect to make it an outgoing TCP connection so it can talk to the internet. And there's some fairly straightforward ways of explicitly and in a very granular way whitelisting in these resources.
Yeah, one thing I was wondering, that if you share a folder, if the folder contains a symbolic link somewhere outside of that folder, right? So will the Pico process interface stop the application from accessing those things, or is it free to?
The question there is, well, once you bring in some actual folder on the underlying host system, it may have things like symbolic links or junctions or anything of that nature, or hard links to resources that may be outside of the expected purview. So in our present implement, we certainly could have all manner of policy. In our present implementation, our default policy is to say that as if the administrator does map in a portion of the host file system, and the administrator is understanding the implications of doing so, and sort of allowing that to happen. Another way of looking at it also is that this is only sort of one way of backing the virtual file system in Drawbridge. The details are kind of probably more than we want to talk about here, but we do have a very generic interface in which you can plug in any virtual file system that may not be backed by the host file system. It may reside entirely within memory. It may be backed by a database, or may be something that is a little bit more controllable by the administrator. This is the default in our present implementation, though. So another important component to our system is some of the data. We've talked a lot about the different runtime pieces. So we have this notion of a Drawbridge package. It is our unit of deployment, intended to be entirely self-contained and also self-describing. So a package, what does it consist of? It includes potentially a manifest that exposes its identity, dependencies it might have on other packages outside of itself, some minimal access control requirements of resources that it needs access to in order to be able to run correctly, and some references to some of the interesting resources contained within the package. So more interestingly, perhaps, are, well, where are the actual files, where are the actual data? So the payload of a package is 0 or more files, registry data in kind of simple textual format, and perhaps even debug resources. The idea being that each runtime component you wish to run inside a Pico process will be packaged up in its own unit that is completely self-contained, has everything it needs, and contains all of the files that it wants to contribute to the virtual file system so that it can run correctly. And I'll show a very quick demo just to kind of visualize this in a few minutes. Everything is a package in our system, and there's on the right here just a very simple kind of excerpt of a manifest of a particular package. In fact, this is the IIS worker process package that we were running earlier, quickly showing you version information, dependencies on the CLR, which is a separate package, and a reference to say, well, here's my application. Here's the actual executable code within my package that you probably want to run first. When the security monitor starts and is asked to launch an application, it's pointed at a package or some set of packages. It goes off and it resolves the transitive closure of all these packages and their dependencies. It then takes all of these packages and it takes all the file content across the different packages and unions them together into a kind of composed virtual file system view that will be presented to the application. So the application has no idea, nor the libOS has much of an idea that this may be backed by various different resources in different locations, or perhaps even different on-disk formats. Similarly, we do the same thing. There was a question earlier about the registry. Every time we launch a Pico process, we create a fresh registry populated by the textual registry content scattered across all the different packages that are being used to launch the application. Also important to mention is that all packages are read-only from the perspective of the Pico process. They're effectively mapped in copy on write, so that the application can think it's scribbling over some of the binaries, but you can safely share these read-only packages amongst multiple tenants. Question in the back?
So are there, can the applications, if the application makes changes to these, can those then be persisted and it can be resumed with those changes that things have made?
So the question is, well, what if the application wants to persist the changes in some way? Yes, so the changes the application makes are actually written to a read-write overlay that is composed on top of these different read-only packages. And it's sort of up to the administrator of the app, of the system, kind of hosting the system, to decide what to allow the user to do with that read-write overlay, and if it actually is shared across multiple processes or so on or so forth. Similarly to with registry data. You may, for instance, otherwise choose to say, no, actually I'm going to throw away all your changes when your process dies, sort of a policy decision. So just pause another moment to see if there are any other questions, and actually want to show you another couple demos to kind of visualize some of the things we've been talking about. Bill.
Try to understand something here. The stuff that the administrator does specifies, say, mapping of the real file system, pieces of the real file system into the... Does that imply that if I want to run this, say, in Azure, that the set of applications that I can run on this thing has to be determined by the administrator because those mappings are trusted? And so I need to have somebody trusted who's going to write the package. It doesn't mean, I get that you get the process isolation, but if somebody wants to come in and run their own application with their own requirements inside Drawbridge Azure.
So the question there is, well, what if someone other than the administrator wants to supply a completely custom application and wants it to get executed? So obviously there's going to be some contract between that user and the administrator around kind of what they'll accept from the user and in what format it will be taken kind of unmodified. So certainly, a user could provide any application they wanted to. Now it's sort of administration policy, various different kind of decision making around how you'd like to structure a package that. They could provide you a loose binary. We can also run a loose binary and very quickly build up a package around it at runtime. A package is really just a virtual construct. We happen to have on-disk representations of the ones that we use most frequently, but it's a virtual construct that implies kind of payload and policy. And so we can run loose executables if the administrator wants to allow the user to post an exe, post a DLL, post a flat folder of files, and we can run that with no problem.
Okay. The security policy part of what goes in that package, then you have to find somebody to generate automatically, or just bottom dice can run loose executables, but only if they can't see the file system, or I don't.
So the way we've built things are that each package is able to contribute files to the virtual file system, and there's really no limitations or there's no need for limitations around that. It's their own sandbox. They should be able to play with it how they want to. In terms of any kind of resources that come from somewhere outside of a package, that has to be controlled by and administered by the administrator.
So you can create an umbrella package that says, here's the capability to say, running an IS application. It needs access to an HTTP web, or the HTTP port and a few things, and then you can let anyone pour anything into that. The administrator defines the container, but they can allow anything inside of the component.
Question?
So you were mentioning the registry information. Is the monitor maintaining a virtual registry?
So the registry is implemented entirely in the Pico process. It's within our user mode kernel. It is a private per process registry, means it doesn't have to be exposed across the trust boundary, across the ABI, and is something that then we can suitably implement the compatibility of within each libOS.
So the registry information in the package is just sort of initialization.
The registry information in the package it's a file with a little tag on it with a hint to the Pico process. Hey, look at this file. It has interesting registry data you probably want to import. That's right.
How do security updates work?
How do security updates work?
Do you have a custom version of security updates for the guest OS?
So it's a good question, security updates. You can look at our library OS as kind of really just another SKU of Windows, much in the same way that all the different kind of, builds of Windows, server core, client, whatever, get serviced. So too we will be servicing our library operating system. And much in the same way that it's an administrative decision of whether or not you want to apply the patches, similarly, it's a decision on which version of the library OS you'd like to allow used or to use for your application. And that we do allow them all to live side by side or next to each other if you had, let's say, an unpatched and a patched version. The reason I bring this up is because there may be reasons why a particular patch for Windows doesn't apply or doesn't apply in practice because of the constraints under which the application is already running. In which case then you get to decide whether or not you want to, let's say, cycle your application and pick up that security update. Updates to all the other components can be done in exactly the same way. The only other kind of components outside that world are our security monitor and our driver, and we'll have some mechanism for patching and providing security updates to those as well.
So, okay. So if there's, say, a vulnerability in HTTP, right, which is in the library operating system, where it's going to be, or have we got it in now?
So,
well, we don't need to worry about that. Imagine that there's a vulnerability in HTTP. This clearly is not a threat to the outside the Drawbridge project because you've isolated it. But me as an application developer, I really care that my company's website is no longer is vulnerable to external bad people. So the way that Windows handles that is we have Windows Update and we push patches out through Windows, and it's a big edifice of complexity and also holes, as it turns out. Do you have something like that in there, or does the application developers each have to go off and do it by hand?
So the question is, well, Windows has Windows Update. It makes it easy. Everyone gets all the updates all the time on Patch Tuesdays, whenever things happen. What about in our world? So probably a longer discussion offline would be useful, but what I will say is our servicing model is very similar to, and what we've adopted is the model that the Windows Azure organization already has. So there's sort of already this existing kind of separation between the affected parties, where in the Azure world you may have the root partition being a component that, well, is trusted, and Microsoft cares very much about making sure that that's really locked down. But the different guest OS images, if you're running Windows as a guest on Azure, well, unless there's a bug in the host, there's really no way you can cause problems to anyone other than yourself as the tenant. And you may be worried then if it's facing, network facing. For that reason, then Azure provides, whatever the periodic updates are. For compatibility and kind of uptime reasons, these updates are not necessarily forced on all tenants, but are made available in some way. I'm a little fuzzy on all of the details, but the model that's been chosen for how the guest OS on top of Azure is getting serviced and running is the same model that we're choosing for really our guest, the library OS. All right, I'm going to jump in a couple quick demos and show you a little bit about what I've been blabbering on about. So first I want to show you a little bit of the kind of visualization of what this virtual file system looks like. So something I'll first do is I'll show you kind of a little bit excerpts of a few different packages. We've got our Windows package for our Windows library operating system, and you can see various different binaries that might typically go under the Windows System 32 folder on your host system. We've also got a .NET 4.0 package, and it's also got a few binaries that it wants to contribute to the System 32 folder of the virtual file system. And what I'm going to do here is I'm going to launch an instance of PowerShell inside Drawbridge. I've colored it green just so you can tell the difference between what's running inside a Drawbridge environment and what's running natively. And very simply, I can show you the binaries that show up in this virtual file system. You end up seeing a composed union view. You'll see these top 3 binaries or so that came from the .NET package, and you'll see the remaining binaries that were contributed by the Windows library operating system package. Now, if I instead had launched, let's say, a command prompt without .NET support, those .NET binaries need not even show up. So we really do have a good flexibility in customizing the kind of the API surface binaries, libraries that are available inside the Pico process, really to what the application running on top of it needs. Something else I can show you is that virtual registry that we were talking about just a second ago. And I can use the nice registry provider in PowerShell to show you the services key on my system, which does have a number of keys populated, but clearly far fewer than what you might see on your native Windows system, where you'll see all the different background user mode services and drivers and so on. Here you'll just see a few of the components that we've actually brought in and have present so that we can support functionality like cryptography and sockets. So that's sort of it for the quick PowerShell demo. Want to show you another demo to kind of illustrates live migration. And Galen mentioned it earlier, but Excel is one of our favorite applications that we've been running for quite some time. So what I'm running here is I'm running Excel isolated inside a Pico process. What you're seeing there was the debug spew from our security monitor I turned on. And something else that you might have just noticed is when I first launched the application, you didn't actually see anything. You just saw this command line interface. That's actually because the application doesn't have access to talk to the window manager running on my host system. So what we've instead done is we've actually run a little remote desktop server inside the Pico process, optionally, of course, not required for headless applications. And we're able to connect to it via basically a networking protocol, much in the same way that you might be able to connect to a virtual machine running under Hyper-V. So here our proxy for showing you that Excel is actually fairly rich in its functionality here is that, look, we can create a very interesting pie chart. So the next thing I'm going to show you is something you probably haven't seen with an individual Windows application, is I'm going to suspend the application. So I've just done a per process hibernation, and what you see here is I've just shown you the size of the dump file that comes out. So this is kind of comparable to the save state file in Hyper-V world. You see, well, it turns out the dump file compresses extremely well. So we end up with compression getting to around 3 or 4 megabytes for Excel. You might get a little bit larger for some beefier applications, but it's really generally in that range of under 10 megabytes or so compressed for a lot of these applications. Now, if I wanted to, if I had another system running here, if I had things set up with Azure, I could flip my dump file up into the cloud anywhere that had a Drawbridge host present, and I could bring the application back to life, and instantaneously, or under a second or so, you have the application back and ready for you to interact with, all of its volatile state preserved, even though I hadn't even kind of persisted anything explicitly to disk within the application. Sort of also important to note here is that all of the applications you'll see and all the applications we've run inside Drawbridge are running completely unmodified with one very minor exception. In the case of Excel and PowerPoint as well, it turns out that our library operating system is not a genuine Windows OS, so we had to disable the licensing checks in Office. Everything else is running with complete fidelity and exactly the same. There's a small list of features that are moved to, that we haven't gotten working yet, and things like printing and similar features we've scoped out for the first version of our implementation, but we'll be there in a second one. All right, so I showed you Excel and live migration. I'll show you just a range of some of the other kind of rich client applications that we've had working. Well, you've already seen Excel. Something else to point out, this is 5 or 6 different Pico processes, all run booted completely cold. These were not resumed from any hibernation file, so you can see that they are launching fairly responsively, and with secure isolation amongst them. We've got Notepad and various different internal applications of Windows that we first got up and running. You can see part of our paper there, PowerPoint for presenting. We have a simple .NET application to show window forms application running, and we've also got Reversi, which is really near and dear to our heart because it was the first application that Galen and Don got working when it was still an intern project. And so one final graphical application I want to show you is Internet Explorer to show you a networked client running. So here we've got the Bing homepage. It looks like the background isn't quite showing up yet, but this is to show you that we can whitelist in access to the external internet. In this case, we allowed internet access to only outgoing connections. So for instance, if Internet Explorer tried to set up a listening socket, it would be denied. But the other really nice thing about using Drawbridge with Internet Explorer running one copy of your web browser in each isolation domain is if at some point you navigate to some website or become worried that there's some malware, some ActiveX control you don't quite trust, you can always kill it just by closing it. and it's gone, and you know that there's absolutely no harm to your underlying host system. Those were the demos of Drawbridge. I'll speak for a quick moment just on kind of where we're going from here. As I mentioned, obviously, we're trying to ship and productize this within Azure. So that's our primary focus as a team. We'll be shipping in the calendar year, primarily working on bugs, improving performance, specifically looking at also resource metering or governance and performance isolation to make sure that we have a good offering there. Secondary goal of ours is also to prep for integration into a future version of Windows. That there are components of our system that belong more in the core Windows operating system, and working with the Windows organization and the Windows Azure organization to make that happen. Also, finally, as I mentioned, there is additional work kind of ongoing within MSR and elsewhere to do other kinds of speculative or interesting things with Drawbridge. There's CloudTop, which was presented at TechFest this year by Brian Myers. It's actually a really neat way of showing, well, what are the kind of user experiences you can build on top of Drawbridge if you have this kind of technology. And we're focusing a lot on the server-side experiences and the hosting experiences in Azure. He's looking more at the kind of the desktop side experiences. So Brian Zill is working on actually taking the entire Windows TCP/IP stack and moving it to run entirely within the library operating system. Today we actually use a virtual I/O stream to communicate with sockets, but moving it entirely up allows all sorts of really neat things like being able to assign an IP address to your process. And Brian actually has a really cool video on IdeaStream showing some of his progress he's made on that so far, so you should definitely check that out. There's sort of other projects. There's an intern project going on. Andrew Bauman's working with an intern on non-Windows library operating systems. There's work on incremental checkpointing, so you can have kind of delta snapshots that Jay is working on along with a former intern. And there's also a project starting up in MSRA to figure out, well, how do we bring DirectX into this world? Right now, we only allow kind of 2D, and we don't provide hardware acceleration. How do we bring DirectX in without compromising our security or isolation? And if you're interested in learning more about Drawbridge, well, you can just shoot us an email, stop by, drop by. We're in Building 109 now, so you do have to walk across the street. But there's also still people here in 99 who are working, and you can tackle one of them, go to HTTP Drawbridge. You'll see various design notes, documents, information on how you can download a copy of Drawbridge and try it out yourself. If you really need to, or if you want to, you can email asdraw, which is our team distribution list, and we'll get back to you. Question?
Yes. Have you run an app compat test to get an idea as a percentage of applications in the world, how many can run on this and how many can't?
It's an excellent question. So the question is, have you done anything to kind of fingerprint the application compatibility that we've reached so far? So as I mentioned, we're constantly working on increasing that, so it is a moving target. We are actually right now underway in building and using some tools to try to capture, for given sets of applications or application workloads, really what's the functionality in the underlying system that they're depending on, at least in some approximate way, and trying to compare that with the functionality that we have working so far. And that's something that's really important to us as we're working in Azure, because as Bill was hinting at earlier, Azure does provide you the ability to upload an arbitrary application of your choosing. Now, there may be certain limitations on the guarantees of how well that application may work if you kind of go off the edges of what's the official supported scenario list. But it's definitely something we're interested in kind of really rationing down on and kind of at least figuring out what we do support. Much in the same way that I know the Windows organization has done a lot of work figuring out, as they provided kind of smaller and smaller versions of the Windows operating system, things like Server Core and MinWin, to figure out, well, what is the functionality set exposed in these kind of smaller subsets. So too, we're very interested in doing the same thing. Question over here. Yeah, along that line, it seemed like you guys had a nice, you'd broken Windows down into components in your demo, because you had one where it was like the normal Windows and then the PowerShell with .NET. And I find that customers are generally pretty ignorant of what their dependencies are. And so when you're saying that you could just upload something to Azure, in my previous experience with customers, if I said, well, what do you depend on? They would be like, Windows. So how do you, like, what package do you tell them to use? Do you have like well, the customer doesn't know, so here's everything? So that's an excellent question. The question, just to repeat it, is, well, a lot of customers don't necessarily know what they need to have in their applications or what their applications depend on. Do you just give them everything? And in so doing, I'm guessing the implicit follow-up is, well, do you lose some of the benefits of the componentization? And the answer is, well, more or less. So to the first part, do we lose the benefits? Not necessarily. So we still have the ability for an application author, maintainer, or for us, if you really know what your application is and its dependency set is, to really trim what's sitting underneath you. It decreases your servicing kind of footprint. It decreases runtime footprint and overhead, and makes it a lot easier for you. That's if you're amongst the kind of, like you said, on the closer to understand exactly what's going on side of the spectrum. The other side of things, it's definitely always possible also to come up with perhaps kind of different slices. So for instance, in the Azure world, we're not going to necessarily provide a LibraryOS package that has everything native Windows does. There are a lot of components that are really just not interesting to run on a server. And there's going to be some cut in saying, well, Azure actually defines an application platform. Along with that platform, you can actually try to pair what runtime support you have in your LibraryOS with the platform you're exposing to customers. And of course, then there's the other end of the spectrum where you can always say, you know what, we'll take a maximal set of everything that we've packaged to date, we'll throw it all together, we'll make sure that the application will have access to all of it, and that will maximize the chances that some arbitrary application that we have no insight into will just run. So kind of, we have our options along the scale. Another question here?
Maybe I wasn't, I was in and out on the talk, so maybe I missed it, but the big applications, the one, or at least I think of immediately when I think of running stuff in the cloud, didn't seem to come up, like SQL and SharePoint and Exchange, kind of things that, like, someone just trying to migrate their enterprise servers to the cloud might want to host them. Can you guys do that? Have you looked at that?
So actually the question is, well, what about all the other services that seem really huge to the cloud? Things like kind of database backends, things like SharePoint. What can we do about that? So certainly we have very broad aspirations. We'd love to kind of provide to a very wide variety of services. We're focusing at the moment, you've seen web servers show up an awful lot here, specifically on front-end web hosting, whether it be ASP.NET applications, PHP, Node.js, kind of scripts, that sort of thing for front-end of cloud applications. In particular, because we've got a customer lined up. In fact, the Azure Websites is a service that went live recently using sort of an intermediate isolation mechanism, with Drawbridge being the intended isolation mechanism when we're ready with our V1. And that's certainly what we're looking at first. Beyond that, we are very interested in looking at more perhaps middle-tier services, things like Memcached, things like sort of business logic services sort of running in the middle. Those as being also very, very interesting. Particularly, we think a great niche for us to get into first are the very high density, kind of small application high density hosting. Then on the farther end of the spectrum, it's kind of the bigger iron components like, well, what about SQL Server and what about Exchange Server? And a lot of the benefits we do have, we feel you can exploit them most with this kind of being able to really pack these things in. I don't know how many different Exchange Server instances or SQL Server instances you can or want to pack into one system. It'd be an interesting exercise for us to go off and try running our those applications inside Drawbridge. It's not on our short list right now, but certainly something we're open to. Question?
So you had performance isolation, resource isolation as one of the bullets in one of your last slides. Can you elaborate on that? Most of the talk focused on security aspects.
That's right. So most of the talk focused on sort of access control isolation and that level of resource isolation. Obviously, another key factor to multi-tenancy and kind of hosting in the cloud is preventing against denial of service attacks and sort of resource hogs and intentional or otherwise. So clearly, performance isolation is something that's important to us. So we've got some amount of work scheduled. We don't have a lot of support in our present implementation to add kind of performance isolation for tenants. So we've got kind of scheduled work that we're planning out before we ship for our first version to add in a bunch of that functionality. Additionally, because at the end of the day we really just are Windows processes, any built-in services in Windows to be able to kind of govern resources in terms of quoting, in terms of kind of hard limits, soft limits, using job objects, even just using kind of using background services to look at performance counters and at least get early warning signs of when processes are going off into the weeds, and within, let's say, 30 seconds just going off and shooting it in the head. A lot of these are similarly feasible with Drawbridge, and in fact should work with no modification whatsoever. So these are certainly like kind of the most low-hanging fruit. Obviously, because we are between the application and the underlying system, we see everything going through, and we are in a good and unique place to be able to implement, kind of more mechanisms to be able to more easily kind of really ratchet down on resource consumption, and that's kind of where that work is going into. Does that answer your question?
All right, let's take the speaker.